Hey, good morning, everyone. Thank you for joining us today. We're having a webinar today about Perc-Rite Drip Dispersal for large systems. And just to respect everyone's time, despite there are a few people still in the lobby trying to get in, we'll get started because, a lot of the beginning part of the presentation is more some formalities. So let's hop right in. So just a few things to go over here. We have quite an audience today. We have somewhere in around 80 or so attendees. If everybody's mic was live, there potentially could be a lot of feedback and wouldn't make for a nice presentation. So we're going to keep everybody muted, but it doesn't mean that we still can't interact. So in your dashboard, I believe it pops up on the top right-hand corner of your screen, there will be an ability for you to ask questions. So the questions come through anonymous, and I am the only one who sees them, and I'd be happy to read them aloud and answer them either immediately or at the appropriate time in the presentation. So if you do ask a question and I don't get to it right away, very likely there'll be topics later on that either may address your question or be a more fitting time to deal with that. So stating that, I'd like to start the presentation today, before we do our really formal introductions, is a poll for everyone, just to kind of get to know one another a little bit. So the first question is, what is your role in wastewater? Are you an engineer, a system designer? Are you an installer? Are you a regulatory official? Perhaps you perform operation and maintenance? Or maybe you are a developer looking to see if Perc-Rite may be a good solution at your project. So we'll give everybody about 30 seconds or so. Okay, great. So the overwhelming attendees here are system engineers, so about 83%. So thank you for that. Our second question is, what is your experience with Perc-Rite Drip Dispersal? Perhaps this webinar is your first exposure. Maybe you know a little bit about the technology, but you're here to learn more. Maybe you've been involved with a project before, or you could have been involved with multiple projects. So we'll give everybody a chance to chime in, another 15, 20 seconds or so. Thank you. So it appears that about 85% of you have some knowledge of Perc-Rite, which is great. So thank you very much for that. Okay, so we have a wonderful group of panelists today. We have Brian Allen of American Manufacturing, who is the company responsible for Perc-Rite Drip Dispersal. We have Craig Heindel of Waite Heindel, who is a terrific hydrogeologist. And then myself, Rob Sarmanian, I am the general manager of Oakson. So today, this slide here is what we're gonna be pointing back to all day. So at the end of the presentation, I hope you can walk away and look at these 3 points and have all these answered for you. So we wanna say that Perc-Rite Drip Dispersal is widely accepted at the state level for all the New England states. There are no regulatory hurdles that you need to be concerned about. Number 2, that you'll find that there is a considerable cost savings when working with Perc-Rite for large flow systems. And we have some great documentation of that. And then lastly, but perhaps not least important, because for me that this is at the top of my list, there's a proven level of environmental protection when you use drip dispersal properly. So these 3 points here are going to be looked upon through the context of the presentation. Perc-Rite Drip Dispersal systems, what we consider large flow, where we get into the commercial grade equipment, is at about 5,000 gallons per day, give or take. So we just wanted to, throw that out there. So when we're dealing with all the topics today, let's think of about 5,000 gallons or more for what we're discussing. So further in the presentation, we are going to break down those points and discuss how to size a large Perc-Rite Drip Dispersal system. We'll go through some permitting and compliance. We'll spend a good deal of time talking about construction. There are many other advantages with Perc-Rite for large systems, and one of them is the ability for future expansion and also phasing different parts of your projects. Then the component of operation and maintenance, and also looking at the technology from a long-term sustainability standpoint. So these are the things that we'll address today. And here's my only attempt to be interesting with a slide other than text and pictures. We're going to look through the lens of case studies of actual Perc-Rite systems in the ground and actual systems that are being built at the moment to make those points about cost savings, about sustainability, about environmental protection. So we're going to look at a lot of case studies today, some of them in more detail than others just for the sake of time, but that is really what's going to drive the presentation. So a quick overview of Perc-Rite Drip Dispersal. In the invitation to today's event, we really made the claim to say, well, we really want folks who kind of know about it. For me to go through all of the nuances of Perc-Rite Drip Dispersal is a 3 to 4 hour presentation in its own, but I want to give you about 3 to 5 minutes of a quick refresher so we're all on the same page. So Perc-Rite is equivalent to pressure distribution under all the state codes, both large and small flows in New England. So it is a pumping system no matter what. So even if your disposal area is down gradient from your equipment, we're still pumping, okay? But need not worry, Oakson will provide sizing and actually source the pumps for you and your clients. So all the aspects we talk about today, we are providing the equipment and also the sizing for that equipment. So here's some examples of some pumps. We have some submersible pumps, we have some suction lift pumps, and then we show a pump station actually built on the bottom right. So what may be either the first or second most important aspect of a Perc-Rite system is the hydraulic unit. The hydraulic unit is placed in between the pumps and the disposal field. The hydraulic unit is basically final filtration. It provides a flow monitoring component. So each of these units will have a flow meter, a totalizing flow meter as part of the package. And then lastly, we have the ability to have zones. So sometimes the zones are built into this unit. Sometimes they might be just downstream of this unit, but we break up the effluent disposal into different areas called zones. So here's some examples. All of them are commercial grade systems. Most of the time for these large systems, they will be installed and placed inside the treatment building. But for systems that do not require treatment, we have a commercial unit that is designed to be just at above grade, and then there'll be an enclosure that will go around it to provide protection and some insulation. So you can see that example on the bottom right hand picture. So our control panel, it's a control panel, right? So, but we have a time dosing control panel. So when a float goes up, it doesn't mean the pump's going to necessarily go on. A float goes up and starts a timer, and we're going to dose the disposal zones on a timer basis. For these large commercial systems, it's going to be a duplex setup. There's touchscreen displays. We have the ability to get in and out of the PLC, so we can dial in or log in through a network and see what's going on, make adjustments if necessary. Also, the ability for the panel to call out or send information out. There are data export features. So if you want to download reports on a weekly or monthly basis, that's always available for our panels. There is a customizable aspect. So if you need, different nuances or different things for them to do, our great folks at American Manufacturing can make that happen for you. They are SCADA compatible. So whether existing SCADA systems inside the treatment facility, or maybe you need something independent that we can provide to you. And then sometimes, but not all the time, there is the ability to integrate with the treatment system, whether it be dose cutoff capabilities, killing lift stations, certain things that, or even control a small scale treatment system, we can do that. So that's, some of the parts of the control panel. So here's the magic behind Perc-Rite Drip Dispersal. It's the pressure compensating emitter. And what that does for us is it provides equal distribution across the entire network of your disposal area, whether it be completely flat or on a slope. We're going to apply the exact same application rate at every orifice along the drip dispersal tubing. And that works because the tubing has a range of anywhere between 7 and 70 pounds. It's going to work to get the exact same application rate. It's about a drop of water every second. And some other things to know about the drip dispersal tubing is that at the end of every pump cycle, every drop of water, or almost every drop of water, will drain into the soil through the emitters. So when the pump shuts off and the pressure drops, then all of the emitters open up and all of the effluent will drain into the soil. So you may ask the question, in northern New England, is there a freezing concern? None whatsoever because of that feature. There are many great flexible installation options. You can see this being plowed into existing grade with a ditch witch. Maybe it needs to be put on a sand bed. Maybe it needs to work in a serpentine fashion. All those options are on the table. There is a component of routine automated flushing so that the tubing is forward flushed, so that any slime growth that may try to grow into this tubing will be returned back for settling. So you're because of that, you're not going to have any clogging concerns. It works well on sloping sites, I mentioned a little bit previously. The diameter of the tubing is only 1/2 inch. This really comes into play when you're looking at finished height. So we're not dealing with, multi inches of pipe or chambers or whatnot. Your finished grade is reduced significantly because the pipe diameter is only 1/2 inch. The typical burial of the tubing is anywhere from 6 to 24 inches. This varies a little bit from state code, but that's the general realm that we like to work in to keep in an oxygen-rich environment. And then lastly, hey, we're manufactured in the good old USA. So this slide could be a full day or 2-day presentation talking about nutrient removal, environmental protection. But what I want to do with this slide is just so all of us can come to an assumption that when you time dose small amounts of wastewater equally distributed in the upper oxygen-rich soils, there is significant removal of nutrients, contaminants of emerging concern, viruses. So some of those nutrients and contaminants would include nitrogen, phosphorus, the fecals, BOD, TSS. Now, there are a lot of peer-reviewed studies that prove this, okay, through NAURA or EPA. Some of these slides and these pictures are provided from the Massachusetts Septic Test Center, run by George Hoyfelder. A lot of you may know George. The barrels are an existing study that we're doing right now, that we're measuring effluent quality at 1 foot or 2 foot below the emitter, and measuring nitrogen uptake, phosphorus binding, fecal BOD TSS removal. It has been phenomenal. And I wish I could share with you some results of that today, but the study isn't complete, but we can look for that in the future. But again, let's just kind of make the assumption that all these boxes are checked. And if you want to see some further proof, we can have an 8-hour presentation in the future, or there's some data and studies available for all of you to look at. Now, Perc-Rite, the relationship. So Perc-Rite Drip Dispersal is a national product. You know, I didn't make it up in my garage. The good folks at American Manufacturing did about 30 years ago. But the relationship is that Oakson is the New England distributor of Perc-Rite Drip Dispersal. So we cover all 6 New England states, and actually we do cover a little bit of New York State. And American is the manufacturer, the patent holder, really the masterminds behind this this terrific technology. So here's a little example from our website of Perc-Rite Drip Dispersal in the regional level, so what we cover for Oakson, but we have a much broader aspect to talk about. So at this point in the presentation, I'm going to turn over to Brian Allen, who is the president of American Manufacturing, and was very gracious to give us some of his time today. So Brian.
Good morning, everyone, and thank you for joining us today for this Perc-Rite Drip Design and Information session. Like Rob said, my name is Brian Allen, and I'm the president and the general manager of American Manufacturing Company. And we are the manufacturer and the integrator of the American Perc-Rite Drip system. I've been with American for about 24 years now, starting in 1997 when drip for wastewater dispersal was still new to a large part of the country. Quick history on drip in the U.S. Early 90s, a group of industry experts went to Israel to see the firsthand how they were using a pressure compensating emitter to equally distribute clean water for irrigation. This team wanted to use the emitters for wastewater, but knew that they would need to clean up the wastewater first. They came back to US with ideas and added disfiltration and started designing the first Perc-Rite systems for wastewater in the United States. Now, the Perc-Rite process is a combination of automatic time dosing, automatic forward flushing of the pressure comp drip tubing, and automatic flushing of the disc filters. Just as important as the process of the Perc-Rite system are the components that are used: disc filters, pressure compensating emitters, and a fully integrated automatic control panel that can easily run and manage the entire process. Everything should be automatic and not rely on manually flushing or back flushing. The drip systems can be as small as 100 gallons per day and can be designed for 1 million gallons a day. It really depends on your application rate and how much area you have available. Today, we're going to focus, like Rob said, on the large systems, which would mean commercial or community size systems. The drip tubing we use will be the same for any size system, as will be the process of time dosing, forward flushing, and disfiltration. This is not going to change. What does change on the larger systems could be simply the size of the filters, the size of the pumps, size of the force mains, valves, etc. American does offer a variety of these larger systems, ranging from 25 gallons per minute up to 250 gallons per minute. Oakson, in consultation with American, will help select the system that is right for the job, based on flow rates, possible future expansion if it's going to be needed, and other site data. Rest assured that the unit will be one that is both efficient and economical for the project. I'm estimating that we probably have several hundred of these commercial community-sized systems in operation right now, dispersing several million gallons per day. American started working with Oakson in 2005, and in the beginning mainly focused on residential drip, but after the first few years, they quickly graduated to the commercial-sized systems which are today. Over the past 16 years, Oakson has really embraced the technology and really grew the use of the technology all through New England. They're still expanding it today and have really accelerated the Perc-Rite growth in that region. This is really a credit to the team at Oakson. They fully understand the sizing of components. They fully understand when and where to use the technology. They'll work with designers and engineers from day one on the design and continue right through installation, startup, and operator training. But it does go further than that. They are always inquiring about how we can advance or make the system and products better. Of course, we never change the Perc-Rite process, but maybe we add a certain alarm feature or a type of data logging or anything that may be useful for a particular job. Either way, they are at the forefront, and I really can't say enough about them and the progress they've made. They're all extremely professional. I will be hanging around for the rest of the presentation, but for right now, I'll just hand it back to Rob. Thank you.
Brian, thank you very much. So at this point, what we're going to do for you folks is we're going to disable our webcam so we really can focus on some of the material. All right, so sizing large Perc-Rite systems. So we wanted to get a kind of a baseline for each state. I'm not going to teach you how to design in your particular state. You all know are experts how to do that. But these thresholds delineate between the small state code or the large system state code. So under the smaller system state code, so when you're under the numbers here in your particular state, we size the Perc-Rite system through a prescriptive manner. So the state gives us loading rates that we utilize for sizing the system. But what's really important about that, all 6 New England states have given Perc-Rite drip dispersal and Perc-Rite only for any drip dispersal technology available. We're the only ones that allow primary effluent discharge through drip dispersal tubing. So we're the only one. So under this number, the state is going to give us a loading rate, but we can discharge primary effluent. Now, stating that, we're going to head into our first case study to show some of these points. Cooper Farm, Littleton, Massachusetts, a 9,900 gallon per day system. That's 100 gallons below that state threshold in Massachusetts. It is a new construction residential subdivision. The original disposal system was a stone trench system. Okay, so they started with a different idea and then transitioned. It's primary effluent discharge, no aerobic treatment at all. It was constructed in 2018. Here's the design of the original trench system. So you're looking at about 75 feet long trenches and about 300 feet wide. So here is all the trenches, and there is the grading involved. So there's quite a mound here. So the developer looked at this and said, that's a ton of fill. You know, that's going to push back my foundations, all this grading, whatnot. We need to try something else. So the engineer came to Oakson, and we provided them a zone layout of 4 zones here that were significantly lower and had less of a footprint. Now, these are skewed a little bit from the original trench design because we're following the contour. So the tubing runs parallel with the contour to best achieve the minimalized impact. You can see some of the grade differences. You have 306 crossing with 298, so we're 8 feet lower, not to mention a significant percentage smaller. So they decided to go with Perc-Rite drip dispersal. So this is a Google Earth image of the site being built. The inner box, inner rectangle, I should say, is the actual disposal field built. So that's the Perc-Rite system in action. The outer box would represent the sizing and area of impact if they maintained the trench system. Now, it's not 3-dimensional. It would stick up a lot higher like a mountain, but you can see the difference here. So what were some of the advantages gained by the developer by choosing Perc-Rite? They used 8,100 less cubic yards of select sand. Originally, they needed a 5-horse, 3-phase pump to discharge. It was reduced down to a single phase 1 horsepower pump. They were able to eliminate a lift station because of Perc-Rite. Significantly less time for the installation. And our finished height was reduced by 4.5 to 8 feet over that area. The developer provided me information stating that conservatively, he saved $175,000 in just material, not even factoring in the savings in time. And that's only for a 9,900 gallon per day system. Here are some of the installation pictures. So pulling in the tubing, doing the underground manifold layout, and then again, pulling in the tubing. Here is the hydraulic unit along with the zone valve. So you can see how they're suspended a little bit, because when they're backfilled, they're going to be at or below grade. And you can see that picture on the right. So this system at only 9,900 gallons per day did not require a building, a shed, none the like. All you see is that small enclosure, one box at grade, and then a control panel. So it blends very nicely into some of these higher end residential developments. So Perc-Rite just under the number. So meaning when you're just under that state threshold, and that typically falls in systems at 5 to 15,000 gallons per day, you can achieve the following: primary effluent discharge, so no treatment. So that would be cost savings for your client. Typically, pressure distribution is required anyway under all our state codes in the region. So you can just slide Perc-Rite right in and meet that requirement. There is no effluent sampling for Perc-Rite. Perhaps there may be some monitoring well stuff that require for your permit that's outside of the scope of Perc-Rite, but essentially no effluent sampling. There's less frequent O&M requirements, and we'll talk about that in more detail later in the presentation. All of the equipment is exterior rated, no building. Very simplified permitting process. We're under the state code and we have approvals in all states. Significant cost savings for the clients. Now, I haven't really done this at previous presentations, but let me put a number on this for you folks. So when we're dealing with Perc-Rite systems between 5 and 15,000 gallons per day, all of our components and our time on site is going to average between $57,000 and $70,000. That includes the pumps, the controls, the hydraulic unit, Oakson support that we'll go through later. So a very small number as compared to what you saw for the savings. So I'm going to pause here. Any questions? Please type in the pane. Okay, so next we're going to talk about performance or site-specific sizing. So this would be for systems over that state code number. So let me just give a quick review of how this applies, because each state is a little bit different. In Connecticut, Maine, and New Hampshire, you are going to, as a designer, you're going to propose your own loading rates. So you're going to provide mounting analysis, site transmission analysis, soil permeability analysis, and then say to the state, you know what, we're looking at this loading rate, here's our documentation, and the state will approve as they deem fit. So sometimes in the codes, or what you as an engineer may ask us at Oakson for a recommended loading rate on similar projects that we've done before, and we're happy to provide you that information. In Rhode Island, you're going to use the prescriptive table for the smaller flow systems, carry it all the way up through what you need. The one difference here is that the loading rates are based on effluent strength. You also have changes in your setback distances as you increase your gallons per day. And then you'll have a mounding analysis requirement for over that threshold. Massachusetts and Vermont have a very similar type of situation where they provide a guidance document for large system design, and they give you, a loading rate based on certain types, classes of soils. So they'll make a recommendation, but that doesn't mean that you as an engineer or soil scientist, hydrogeologist, can provide your own documentation and recommend a different loading rate. So we've seen many Perc-Rite projects in both of these states where that has been applied. And similarly, you'll need a mounting analysis, that site transmission analysis as well. So, stating that, let's go into 2 case studies kind of wrapped into one, and we're going to transition into a different voice here for the presentation. So case study number 2, Bromley Mountain Ski Resort in Peru, Vermont. It is an 80,000 gallon per day project. It's considered a residential application, so the mountain is building additional ski housing for some of their customers. In order to achieve this permit, we needed to provide a pilot study to show phosphorus removal, and we'll go into that detail more. All of the tubing for 80,000 gallons per day is to be plowed into existing grade. There's going to be no select fill requirement here. So imagine that. There's going to be phased in treatment. So ultimately, we need to provide tertiary treatment for this facility. In the Vermont IDR, folks provided a capacity determination approval in 2018 and carried that through to today. This project has not been constructed yet because the folks are looking for investors and whatnot, and then I think the whole COVID pandemic has caused a little pause on some of this. The second case study we're going to be looking at during this next segment is the town of Bridgeton, Maine. It's a municipal project of about daily average flows of about 116,000 gallons per day. There was a hydraulic capacity loading rate determination, so the state wanted the design team to provide a recommendation for what the loading rate is, and we're going to see that whole process in detail later on. It's only a secondary effluent requirement. Construction has already commenced with as far as clearing and whatnot. The Perc-Rite system is fully fabricated, ready for shipment to the site, and construction is going to begin this summer. So, with no further ado, we are going to pass over the presentation to Craig Heindel of Waite Heindel Environmental Management. Okay,
hi folks.
Take it away.
Hi, this is Craig Heindel, consulting hydrogeologist at Waite Heindel Environmental Management in Burlington, and Rob asked me to talk about the hydraulic capacity considerations that need to be addressed for large-scale systems, and so that's what I'm going to do for you today. There are really 3 independent capacities that should be considered, and your site approval is going to be limited to whichever of those capacities is the most limiting. That's how I think about it. There are 3 of them. Let's go through them quickly and then one by one. The first one is where there is sufficient application area. Sometimes that's called the loading rate. Rob has talked about that a little bit already. Do you have enough horizontal area to take the wastewater that you would like to apply? Second capacity needs to be consideration is the height of the induced groundwater mount. This is the mounting analysis. And the reason that's really important is that the application of wastewater to the site must not allow the water table to rise high enough so that the distribution pipes, the drip pipes, are in saturated soil. They're not going to work in saturated soil. You're not going to match code requirements. This would be true for conventional stone pipe and stone system also. So there needs to be a freeboard of some distance below the drip pipes that stays unsaturated. So that's the second capacity that needs to be determined. And then in some jurisdictions, there's a nutrient loading question that needs to be addressed, sometimes called the carrying capacity of the receiving water. These large systems are essentially indirect discharges to surface waters. In New England, we all know that the groundwater flows towards surface water generally, and it becomes an indirect discharge to that surface water. A recent Supreme Court decision, the Maui decision, has confirmed that it's appropriate to consider groundwater discharges that may be eventually discharging to surface water as discharges. So in some jurisdictions, the nutrients that are carried by that wastewater transmission needs to be addressed. Not in all, but in some. Let's go back to application or the capacity number one, the application area. As Rob said, most of the application rates will be either recommended or prescribed in your code. Typical ranges are as low as 0.2 gallons per day if you have a silt loam, and at the high end of the application rates for sands and gravels, 1 gallon per day per square foot or higher. Could be 2 to 3, 4 gallons per day per square foot. There's a range there, and that's a capacity that you're going to need to figure out. And then once you know your application rate, then you obviously would apply that to determine the size needed for your design flow, or the other way around, you know the area that you have available and you back into your maximum design capacity. The value of the benefit of drip dispersal is that you calculate the application area over the whole tubing area. The tubes are typically spaced 2 feet apart. The wetted zone from each hole, it goes out about 1 foot or 2. So you just calculate the wetted area as 1 foot beyond the outer drip pipes. There's no need to exclude the between trench areas that would be needed for a conventional calculation for a pipe in stone system. On the other hand, you don't get to include sidewall areas. Some jurisdictions allow the inclusion of sidewall area of trenches. Of course, there are no trenches here, so you don't count that. But in general, the area that's available, you can dispose of much more wastewater by drip than by the conventional trenches in the same area, because you're using the entire square footage. And then while you're laying this out, consider the value of having multiple subzones. You saw that on Rob's slide earlier of Bromley. There are 4 zones there. Bridgeton has 6 zones. Many of the larger projects are in subzones, and there's a lot of benefits to do that, and you're going to want to include that concept in your layout. You want to have some redundancy. That'll give you some maintenance flexibility. If there's a problem in one zone, the other 3 or 4 or 5 zones can carry on while the problem in that one zone is repaired. Some codes require some redundancy, and if you have multiple subzones, they each can very likely be served by smaller pumps, rather than trying to serve the entire system with one much larger pump. So it makes for a much more efficient hydraulic system. That's it on application area. Let's look at a couple of examples that Rob already went through. We're going to go through a little bit more detail. Here's the Bromley ski area. They're looking to expand the residential housing near the area, and there's a spot you can see, the black circled area there, that happens to is a glacial deposit, glacial sands and gravel outwash, the Cane Terrace, deep sands and gravels, which is pretty unusual in the Vermont mountains. So they were lucky that this was nearby. There you can see it there, and the circled in black is the open field and the potentially usable area. Very faintly, you can see the contour lines in the behind it. This is a significant rolling topography. It sloped significantly from the upper left down to the lower right, and even in the field, it's rolling across the field. So it would be a very difficult site to lay out conventional pipes in stone. There'd be a lot of cutting. You don't want to fill. Most codes don't allow large systems on fill, so you'd be cutting only, and you'd have to find, you'd be cutting down toward the water table, and then you'd have to find a home for all the material you cut. So this rolling terrain is really well suited for Perc-Rite, because it's just the pipes are cut in at a typical depth, say 6 to 12 inches below ground surface, following the contours of the terrain. Here's the upper soils. You can see it's a sandy loam. Below the bottom of the tape measure is 15 to 25 feet of unsaturated sands and gravel. So very moderate permeability, and no extra fill was needed to be brought in. We just sliced the pipes. The pipes will be sliced in at perhaps that depth at the bottom of the A horizon, top of the B horizon, and there you go. So that's circled in red is the area that was chosen ultimately for 80,000 gallons of capacity applied at 2 gallons per day per square foot. The full build out will require tertiary treatment because of the phosphorus limitations that are in the Vermont's rules. Phosphorus limitations on the receiving water. And in this case, we're up in the mountains, so the receiving water is a tiny little stream, so there's not much dilution, so we really have to knock down phosphorus. There are the zones you can see. It was also on Rob's slide. So that's the Bromley site. Again, very deep sands and gravels, high permeability, deep to water table, and no imported fill. It's an open field with rolling terrain, which is really well suited for a drip type system. The second example is in Bridgeton, Maine. Here you can see the selected disposal site on the west flank of this little mountain, Mount Henry. So it slopes from right to left, from east to west down. It's glacial till. So there is not a tremendous amount of natural in-ground capacity at this site. So we had to bring in, we're going to have to bring imported fill to meet the design demand of 116,000 gallons per day. Here you can see the faint red lines are the ground contours. I've sort of generalized those from the even fainter black lines that are the 1 foot contour intervals from LiDAR survey. But you can see that it slopes from right downward toward the left. We're orienting the drip dispersal fields to be parallel to the contours so that we have the long loading rate to minimize as much as possible the height of the induced groundwater mound. We'll zoom into it a little bit further, and you can see there, you see the test pit log there. We got about 1.5 feet to seasonal high water table at that test pit, 2.5 feet to firm till. That's pretty typical on this site. So the dispersal area is 600 feet in the north-south dimension and about 150 feet wide, 3 subzones. Only 2 of them will be operating in, or really 6 subzones broken up. You can see the slope is about 7%. So you do want to have a sloping site. We'll talk about that. Comes into the induced groundwater mound calculation. So this is the layout was laid out this way. So it's again 600 feet in length, 150 feet wide. We've got 6 drip zones, 3 here that are 300 feet in length, 3 to the north, also 300 feet in length, and about 3 feet of imported sand is being brought in because the natural soils don't have enough capacity to handle the 116,000 gallons per day. So that's the application story, which leads into, as I mentioned before, this second capacity, which is induced groundwater mound. Again, and that's because we need to document and convince ourselves that the induced groundwater mound will not cause the drip pipes to become saturated, to be in saturated soil. Evaluation options, you're probably familiar with them, or you've got hydrogeologists and soil scientists on your team that will work with you. Darcy's law is a pretty simple algebraic calculation. It's often quite adequate, and I like to use it because it's a little bit conservative, and you want some levels of conservativeness in these calculations because you don't have a lot of room for handling spikes of flows. So a little bit of conservatism is appropriate in the mounding analysis. If you want, or if the regulators ask for, you could consider more complicated calculations like the Hand-Tush equation or numerical or analytical models to determine the induced groundwater mound. Let's go back to the simple Darcy's law. You're all familiar with that, Q equals KIA. And so you're going to need numbers for all but one of those parameters, and then you're going to solve for that final parameter. And it could be that you're going to be handed a design flow, and then you're going to determine whether your site can meet that design flow. Or perhaps you're going to want to calculate the maximum capacity for induced groundwater mounding at your site. So you're going to know all of the other parameters, and you're going to solve for design flow. You're going to need to determine a saturated hydraulic conductivity of the receiving soil or transmitting soils. You can do that from literature values. You could do that from actual field testing. Perc tests are not really appropriate, but there are small diameter hydraulic conductivity tests that can be conducted in the field. Those are going to be conservative. You could consider a larger whole soil permeability test or a pilot test, but in some way you've got to come up with a saturated hydraulic conductivity value. Hydraulic gradient, if you're on low permeability soils like the Till site in Bridgeton, then the slope of the ground surface is a good proxy for the gradient. If you're on deep sands and gravels, the ground surface may have little or no relationship to the slope, to the hydraulic gradient of the water table below. So you're going to want to do borings, install monitor wells, measure water levels, and then develop a groundwater contour map and use that to determine your hydraulic gradient. Cross slope length of the area is going to be either chosen by you as necessary, or it's going to be determined by the site constraints. And then H, the thickness of the transmitting zone in Darcy's law. Obviously a thickness has got a top and a bottom. The bottom, the hydraulic bottom of your carrying zone, your transmitting layer, is going to be whichever is shallowest, either the dense soil layer, so perhaps on a till site, that's the dense till, or bedrock, depth of bedrock, or seasonal high water table. In New England, we need to take into account seasonal high water table, which a soil scientist will be able to identify you in the field by examining the soil conditions. So that's the determination of the bottom of the transmitting zone. The top of the transmitting zone will be whatever you choose as the depth below the dispersal pipes. That is the maximum height you'll allow the groundwater mound to rise to. And I like to put in at least a half a foot of so-called freeboard unsaturated zone in our calculations. The regs may require in your zone, in your jurisdiction, they may require a greater unsaturated zone thickness. So you need to work that out with your regulators. And that's again because you need an unsaturated zone for the dispersal pipe. So here's a pretty simple, Darcy's law, of course, is algebraic, so it's pretty easy to do the math. And this is at the Bridgeton site, and so I determined that the upper soils above the dense till could only have about 11,000 gallons per day capacity. That's only 10% of what we needed. So we quickly realized we've got to bring in some select fill. And they had not yet determined which fill that was going to be. So we worked up a table of possibilities depending on the K value. The K is the hydraulic saturated conductivity over on the left, and then calculated the final fill height by just using Darcy's law again and adding a half a foot safety buffer, in this case a freeboard. So that's the kind of calculation that you would do with Darcy's law. If you're using hand tush or an analytical numerical model, it'd be a little bit different. You need to come up with an induced groundwater mound of some sort. And then finally, nutrient loading. Typically, some jurisdictions may be concerned either about phosphorus or nitrogen loading to the receiving water. And one option to determine that, and it's the one that we used at Bromley, is to conduct a pilot test. We actually built a very small drip dispersal system in one portion of the proposed field and applied wastewater effluent to it. The goal being to document, or at least to evaluate, the degree of nutrient removal would be available. I was pretty confident on this site we're going to get a high degree of nutrient removal, but that needed to be documented. So we constructed a little leach field, a little drip dispersal area. In one area, of the site. I chose this spot because it was one of the shallower places to water tables, about 12 or 15 feet here. Other places on the site were much deeper, and it had a monitoring well already installed nearby, right down gradient, that we could sample from, one up gradient. So here's down in the far corner there, you can see the disturbed soil. That's where the pipes have just been cut in. You can see the rolling terrain on this open field. It's be a tough site to do conventional pipe and stone. There's the pipes being cut in. Again, you can see the rolling terrain. The trench is curving because he's following the topography. There are the pipes about to be backfilled. Pretty simple system, just lay it on the ground because this is a pilot system. We had to run it for 4 months to get the equilibrium, but we avoided freezing conditions. To supply it with effluent, we just installed a little plastic lagoon. This is all the pumping system at the top of the hill. We had daily or deliveries every couple of days with a tank truck that brought in secondary effluent from the already existing wastewater treatment plant. And we diluted it somewhat to do a rough mimic of tertiary treatment. Although the dilution didn't bring it all the way down to tertiary levels, but it was at least conservative. And then we spiked it with bromide as a tracer, a conservative tracer, so that we could watch the unfolding of the process of the drip applied wastewater finally reaching the water table. And so the initial, here's a depth of to groundwater. Depth below ground is on the left. The horizontal axis is time. And so when we started, we were just shy of 16 feet to water table at this site. And in about a month, we had developed the induced groundwater mound about 3 feet in height in about 30 days. But that had not yet, although we had reached physical equilibrium of the induced groundwater mound, and it stayed the same through the rest of the study, we had not yet reached chemical equilibrium. We had to go another 3 months until the bromide tracer, that's in blue, the bromide tracer finally stabilized. So you can see for the first month, we were not getting much bromide tracer at all. We knew it was eventually going to show, and there it started to show after about a month. Slowly rose, and then we had the final 10 days or so of leveling off of the bromide tracer, and that's when we then sampled the down gradient monitor well for the nutrients to see how the soils renovated the nutrients. And there you can see the bromide tracer concentrations is the first column, then the nitrate and total dissolved phosphorus are the middle two columns. We started with those numbers there, and then we had several months of eventually achieving equilibrium with the tracer, and then the final numbers you can see pretty clearly there. Not unusual. We had about a slight increase, a fourfold increase in nitrate, as one would expect, starting with the initial effluent, where most of the nitrogen is not in the nitrate form. But we were pleased to see that it only jumped up fourfold. That was great. And then we had essentially total adsorption of phosphorus, mineralization of phosphorus into the soils, which is not surprising. The drip pipes were way up high in the soil profile, where there's a tremendous ability of both of these nutrients to be removed or at least knocked down by different chemical and microbiological processes, but nonetheless, they're handled very well. And the state agreed and authorized 80,000 gallons a day, as you can see in this capacity determination letter. As Rob said, the site has not yet been built while the developers are searching for investors. So there are other options. If you have a nutrient loading requirement, nutrient loading evaluation, other than the pilot test, you could look for literature studies. You could perhaps find a similar site that's already constructed that has monitoring data and see if you could generalize those data to your site. You could try predictive models. I haven't seen much success in that because they're so site-specific. Soil chemistry, effluent chemistry, everything is very important in this nutrient reduction. So I'm not sure about predictive models being accepted by regulators, but there are other options, as I've said, as you can see listed here. So again, you're going to need to evaluate 3 separate hydraulic capacities, and you're limited by whichever of those capacities is the most limiting: application area, groundwater mound, and nutrient loading. And they're really, those capacities really applied to evaluations of all on-site disposal systems. They're not particular to drip dispersal. Again, just to summarize the application area, you're probably going to use either an allowable application rate or one that comes from a guidance document, and then you can calculate it on the entire wetted area of the drip field. So the benefits of Perc-Rite drip dispersal is that compared to pipe in trench, generally the overall footprint is significantly smaller than a conventional pipe and trench system. It's got the tremendous flexibility to accommodate rolling topography, even to, if you have a few prized trees or boulders, you can just avoid those with a piping system. So it's very flexible for installation, and then it's got the benefit of allowing multiple zones for all of those important aspects. For the induced groundwater mound, the goal is to ensure that the drip dispersal pipes always are operating in unsaturated soil. And there's a bunch of different ways to determine the IGM. The benefit of the drip system, like such as Perc-Rite, is that the pipes are installed quite shallow in the soil profile or in the imported fill profile, so that you got as much room as possible for the induced groundwater mound. And then finally, in some jurisdictions, you may need to do an evaluation of nutrient loading to the receiving waters, and options are the pilot test or other methods to document the degree of nutrient removal. And the benefits of a shallow laid perc system is that because it's the effluents applied high in the soil profile, you're going to get the greatest removal of nutrients because of the microbial activity and the higher amount of organic material, humic material, and aluminum iron coatings on the soil particles, and the frequent short duration dosing cycles, which are greatly amenable to contaminant removal. And so I will stop there, see if any questions, and turn it back to Rob.
Thank you, Craig. Thank you very much. So let me just switch back here. Okay, moving on. So based on Craig's presentation, we talked about sizing, right? So now you as an engineer, you've done your soil analysis and your hydrogeo study, and now you have an area. It may be perfectly rectangular. It may be shaped like the state of Texas, but no worries, because you will work with Oakson to take whatever area is available to you, and we will adapt that to a functioning Perc-Rite drip dispersal zone. So you can see the example here, a very odd shaped multiple zone system. That's just for plan view, and then we'll provide you the accompanying detail that will show where the valves are, the size of the pipe, the size of the lateral connections, and whatnot. So all of this is done by Oakson on your behalf. Sizing the pumps in the hydraulic unit. Brian mentioned that in his presentation, that you don't have to worry about that. But what the good news is, you don't also have to take our word for it. We're going to provide you a spreadsheet of friction loss calculations with all of the criteria of your project in it, and give you the math for how we got to the bottom line of a zone supply line of being 2-inch, or a pump being 1.5 horse or 3 horse. And then we'll give you all that information. Then we'll give you all of the details for that selected pump or hydraulic unit that will be in your project. There is a full suite of AutoCAD details, including all the construction notes. On the smaller scale, large flow projects, they can typically be brought in 1 or 2 sheets. On the larger scale projects, we'll break it down into more cut sheets and a different type of presentation so that you can capture all of the nuances that you need for your system. When it comes time for submittals, we will have and provide to you every single possible cut sheet and shop drawing you need. So that hydraulic unit that comes factory tested and delivered to site, all of the individual components that make it up, you'll have cut sheets for, so you know exactly what we're getting. And then if your project does require some specification documents, we have a lot of those available now and can customize them as needed for your projects. For installation, some projects, the one in particular that we're working on at Bridgeton, had a component of a full installation manual. The technologies for this project were chosen before the contractor. So since Perc-Rite was chosen as the disposal mechanism, we provided a very in-depth installation manual that was part of the bid package, so the contractor can bid on it but feel comfortable with what their role is for the installation. So here are some excerpts of the pages from the Bridgeton installation manual. Any questions? Great. Let's talk about construction. Very important point here. Every single Perc-Rite system, and that even includes your 2-bedroom residential repair, which is not in our scope today, but every single Perc-Rite system distributed through Oakson in New England will include technical support, meaning we are not going to drop ship goods to the site along with that installation manual and say, have at it. We are sending our trained technical staff to assist the contractor when installing the Perc-Rite components. It is a very in-depth process that shouldn't be glanced over, because this is a really value-added component of when you choose Perc-Rite Drip Dispersal. You're getting the expert assistance along with it, starting with a pre-construction meeting with the site contractor. It could be an actual site meeting, or during the last year we did a lot of Zoom meetings, and with that we've created a whole series of video tutorials that you can see on the Oakson.com website, or if you go on YouTube and Google and put in Oakson, there is a whole series of videos that show how to install the different components of a Perc-Rite system. Now, these were done at smaller scale projects, but as Brian said, it's the same pipe, it's the same process, just scaled a little bit larger. But the direct on-site support from our technical people when they arrive on site, we're going to assist in the manifold fabrication. So we're going to make sure that everything is being built correctly into the specs on the plan. We are going to assist with the drip tubing installation. We're going to make sure all the tubing goes in at the proper location and lined up correctly with the underground and the manifolds. The hydraulic unit, which it comes pre-assembled, so the actual plumbing of it is not that challenging, but we want to make sure that it's done correctly. We're going to oversee that along with the pump and float installation. And then finally, when everything is complete and done, Oakson will provide a clean water system startup, for which we will provide a letter of certification to the engineer to provide to the regulatory officials and get your compliance documents complete. So Oakson involvement with the installation is kind of broken up into different parts, and this happens over different days. So one of the first parts that we do is we deal with the underground. So all of the force mains and stuff, the contractor can run those themselves. We don't need to see trenches and, hundreds of feet or thousands of feet of pipe in the ground, that's all going to be tested after installation. But when it comes to reaching the side of the disposal area where the manifolds are being built, that's where we're going to hop in the driver's seat and make sure that all of the manifold underground is built correctly, insulated according to the specifications, and then backfilled properly. You see here the middle picture, the tubing is actually already being attached to the manifolds. These pictures on the right, you can see again, prior to backfill what it looks like. And then after backfill, you notice that we leave some pipe sticking up out of the ground. That's by design, so that now when the vibratory plow comes in and starts pulling lines, we have a good reference point to make sure everything lines up properly. And then again, after that, all of these will be connected to the actual drip dispersal lines. The drip tubing installation on these large scale projects is done by typically vibratory plow. And we have worked with a number of irrigation contractors that are willing to travel. So if you're worried about in your area that there isn't this type of equipment available, or the contractor may not be skilled for it, we have relationships with several irrigation companies that you would be surprised how economical and cost efficient it is to hire these folks as subs. They know the equipment, they know the tubing, they know how to do it. They can put it in twice as fast as anyone else, and so the final cost ends up being less expensive than trying to do it on your own if you don't have the experience with the equipment. So you can see here the tubing attached, ready to go into the soil. A couple runs ready along the process, and then the pipe sticking up out of the ground and lining it up properly. So at this point of the presentation, I'm going to show a 3-minute video that has no audio, so I will be your narrator during the process and describe to you what's going on. So let me fire that up. Having a little technical difficulty. Oh, that's unfortunate. All right, let's try again. Here we go. All right, so this is a little bit boring, but I wanted to demonstrate to you how simple it really is. So you have the machine backing up to reattach to the coil of drip tubing. So there is a little chain link that they're just going to wrap the tubing in, duct tape it to itself, and then go from there. What's the most time-consuming part of the drip tubing installation is actually just, backing up and tying on to the next piece. Once the vibratory plow is in action, it's only a minute or so to travel across the length of the field. So in the case of Bridgeton, we're going to be traveling 600 feet in one run. This tubing is going to be pulled in a lot quicker, perhaps, than if you have 40-foot long runs and have to cut it off and then back up or spin around and reattach. So here's the plow dropping in the ground. You see a string line attached to a stake that the operator is riding along the tire. That's going to make sure that he is driving along a straight path to keep the tubing uniformly installed into the fill material. The tubing comes off of a spindle coil, which makes it, the operator can go as fast as he wants. This is about 125 feet long pull. And once he's attached and goes, it only takes him about 90 seconds to go across. The whole process of backing up, reattaching, and going is maybe only about 3.5 to 4 minutes per run. we're going to transition from this perspective of the installation for this site to a drone capture video. So we got a drone last year, and it's been great to really capture the installation process. So I've sped up the video so that we don't have to be here for forever. But you can see how the operator gets to the end, and he pulls it up, cuts it off, and he's going to back up. But there are other people walking around on the ground. So as the plow finishes the job for this particular run, people are moving stakes, reestablishing that string line, now looping the tubing together, or perhaps tying it into the upright. So only 2 or 3 or 4 people in the process are able to advance the installation at a very quick and efficient pace. This is a system, quote unquote, just under the number, about 8,000 gallons per day in Massachusetts. All of the drip dispersal tubing was installed in 5 hours. So hopefully you enjoyed that. And let me head back to the presentation. After the tubing is installed, we'll go through the process of actually adapting the tubing through some barb connectors that go into PVC that will attach into that underground pipe, for the distribution laterals. You can see the example of what's called a top feed manifold here in the top right-hand corner, and the bottom right-hand corner are for systems that require the tubing to loop to itself and perhaps have all the underground and manifold connections only on one side of the disposal zones. The hydraulic unit, again, they come factory tested and come to the site ready to be connected. So the example on the left is a system that does not require a building. You can see it blocked up above ground, so all the underground can be achieved at below frost depth. And then the picture on the right-hand corner is everything backfilled, ready for the startup. The bottom right-hand corner is a system inside a treatment building that's being connected. So it's not all quite finished yet. So you see a lot of things, all in the process. But again, it comes fabricated on aluminum skid plate, drops into the location you need, and then all of the different connections to the zones or the pumps or the return line will be established. Pumps and floats, not much to say here other than the type of pump setup. We will work with the contractor to make sure it's done correctly. You can see the duplex pumps from a bird's eye view, from down in the tank view, and then a dry view, so you can see how they're all kind of put together. So heading into case study number 4. This is Prescott Point in Portsmouth, Rhode Island. The entire residential subdivision is 67,000 gallons per day. Like the example in Bromley, this tubing was plowed into the existing grade with no select fill being imported to the site. This project started in the late, I think 2005 or 2006. They built a treatment building for a direct discharge into the bay. The developer kind of lost his funding and went belly up, so that the actual treatment facility was never even turned on. So we have an existing building with a direct discharge permit that could no longer be utilized because of the regulations and whatnot. The permits expired. So the new developer who took over had a great idea with his engineering staff that they wanted to go with Perc-Rite Drip Dispersal, discharge primary effluent for the first phase, take that abandoned treatment building and modify it for something that they can go in ground with, and then use proceeds from the sales of phase 1 to help develop future phases. This project was constructed in 2015 and has been online since. So here's a Google image of Prescott Point, so you can see the proximity to the water. Here is a more zoomed in version of that. So this is the existing treatment building prior to Oakson's involvement. These are the actual zones that were built, not uniform by any means. And there are a few more zones over here. So they decided to go with the most suitable areas of soil to build their zones, which, obviously makes sense. Here is the abandoned treatment facility. It looks pretty good, but they cleaned up. There was some vandalism. Unfortunately, there was a lot of rodents that nested in there and ate a lot of the wiring. So a lot of the components, really, to even utilize them again, it was going to be more of an expense just to start from scratch with a lesser level of treatment that was to be required. Phase number 1 was up to 15,000 gallons per day. So they reconfigured the tanks in the treatment process to turn it into just a septic tank effluent system. So there was solid settling that carried over into pump stations. They built out all of the Perc-Rite components in phase 1. So even though we were only discharging 15,000 of the 67,000, so about 20% or so, it was important to have all of that soil capacity because the prescriptive loading rates under the state code required that. Also, when they did the site transmission analysis, they backed into the nitrogen loading capacity. They were able to get 15,000 gallons per day before the nutrient loading did not meet the code requirement. During the process of phase 1, the engineering company redesigned the entire treatment train to be ready for future phases. So this slide's kind of interesting. This is, that same slide I showed you before, but you can see the actual plan layout, how these pieces, just like a puzzle, fall right in. So it's quite exact on how the tubing was installed, even with the vibratory plow into existing conditions. So the tubing is being plowed in here. Now, this may look to you like it's a fabricated sand bed. It is not. What was a great idea by the team was this is what the entire site looked like. It was overgrown brush and whatnot. So they took a dozer and just skinned off the O layer and all of the organic material to get to that transition where the A layer began, made a nice smooth finish so the vibratory plow could do its job and follow contour very consistently. So these are 300-foot long pulls for 2 of the zones. And it was achieved in only a matter of a day or 2 of the entire disposal system being installed. This is the treatment building. So we utilized a corner of the building with close proximity to a hatch where the settled effluent came in, and through suction lift lines and pumps, drew it out of those holding tanks through this hydraulic unit, a force main into a series of zone valves. So this represents all 6 of the zones. So these particular zone valves will turn on and off as needed, only dosing small areas of the entire disposal field, all done by the control panel. So all of the electrical components and all of the items that may require routine operation and maintenance, all inside the building. Very, very simple process for the operators. So what were some of the advantages brought on by this project in the changeover to Perc-Rite Drip Dispersal? They were able to take the existing infrastructure and easily adapt it for Perc-Rite. But I kind of say is that the Perc-Rite system was very easily adaptable to the infrastructure. No select fill was required for any of this disposal fields. There were some irregular shaped zones that were needed to conform to what the most suitable areas of soil available to the site. No treatment was required for phase 1, significantly less time for installation, and the developer used sales proceeds to fund the future phases. So, phasing, that's a perfect segue to talk about what Perc-Rite can do to help your projects for either factoring in phasing or phasing and treatment. I'm going to pause just for a second because it looks like some questions might be coming through. So let me see if this is an appropriate time. I will get to those later on, but great questions. Thank you, everyone. So, expansion and phasing with Perc-Rite. Typically, Perc-Rite is the least costly part of a project. So when you think of the scale of treatment buildings and treatment, it's usually 7 figures with some of these treatment components. Perc-Rite is typically, 10, 20%, even less sometimes. I've already given you the example of the cost of some of the systems that fall below that state threshold number. I know this has been redundant, but primary effluent discharge is approved in the region and is a tool in your toolbox. We can phase in treatment. So start with primary discharge, phase in treatment. Another great advantage is that future drip zones are very simple to add. So when you think through what your possible expansion could be, you could stub in some force mains in the same trench with the force mains you need to get started for future drip zones. So really it's important to think through the process. So size your pumps, size your zones for what your full build out may be down the line. And what Oakson brings to the table here is that we're thinking big picture with you as a designer. So we're going to ask those probing questions to say, hey, is this, maximum what you have for the site, or does your treatment facility have more capacity built into it? Should we think about adding in a zone or two capability to the control panel or the hydraulic unit? They're just simple things to think of that are very, very low cost on the front end to give great flexibility later on. That brings us into case study number 5. Hume, New England is a Christian camp based in the Berkshires of Western Massachusetts. It is a facility at 25,000 gallons per day, which puts us into the large system threshold under the Massachusetts groundwater discharge guidance regulations. It is a retreat / campground facility. It has very seasonal flows and also varying flows depending upon weekend functions in season or weekend functions off season, but there are maintenance people there all year round. So the flows vary from time to time, whether it be during week or even during season. We built an expansion into this system, so we'll talk about that a little bit shortly. This brought a very low impact footprint to the site. Now it's a very beautiful wooded area, with lakes and nearby other amenities. And it was important from an environmental standpoint that the facility not only wanted to keep that environmental aspect viable, but it was a condition of building this system to have a very low environmental impact to the area. The system was built and started up in 2018. So let's look at this. The groundwater discharge regulations in Massachusetts have a guidance document for loading rates. This system and the soils there were 22 to 25 minutes per inch percolation rates. And if you look at the guidance document, Perc-Rite has the smallest footprint available of any other disposal areas or any other disposal systems under the document, meaning that by choosing Perc-Rite, the engineers loaded the system at 0.75 gallons per day square foot versus 0.2 gallons per day per square foot. You may ask why. Well, the good folks at Mass DEP realized that because of the low application rate, because of the rotating zones, because of the run time, rest time, and the recovery that the soils are given through the benefits of Perc-Rite, that for slower perking soils, they were able to give it a more, I don't want to say aggressive loading rate, but I guess I did say aggressive loading rate. So in this case, the inner rectangle are the 4 zones built for this system. The outer rectangle represents what the area of impact would have been if they chose any other disposal system under the guidance document. So I just kind of centered this, but you can imagine that if they didn't want to move the building or the other infrastructure, this would have slid out and all of this wooded area would have been decimated, not to mention way more fill to achieve the separation required. So just real, I just wanted to pause here. 125,000 square feet of impact versus just under 34,000 square feet of impact. So expansion, the treatment facility and the treatment system could accept additional flow than the 25,000 gallons per day that we built initially. So you can see the hydraulic unit installed. Each one of these Schedule 80 pipes sticking up through the foundation, through the floor of the building, represents a zone or a future zone. This happens to be the common return 1, 2, 3, 4 zones. Here is expansion 5 and 6. So these are brought outside the building in the same trench about 40 feet outside the building. So when it comes time to expand, they don't have to disturb any of the area or infrastructure around the treatment building. Also, you have 4 zone valves here. Here are zone valves 5 and 6. So when the time comes, easily plumb these in, connect them to that existing force main stub through the floor, build your future zones, and there you have it. You have expansion simplified in the building. This did not cost anything to add in this expansion, just the cost of the pipe. A couple of zone valves later on. Piece of cake, low cost for the campground. So during the installation process, you can see here pulling the tubing in. They adapted a skid steer to do that. Not a problem. The contractor was very adept at doing a lot of different site work, so they pulled the tubing themselves and did a heck of a job. Here are some of the manifolds being constructed prior to backfill. And in a recap of this case study, what were some of the advantages? Well, this is a conservative estimate. 18 to 20,000 less cubic yards of fill were used because of Perc-Rite under this guidance document. Significantly less trees were cleared. We have 50% expansion built into the system with little to no cost. Significantly less time for installation, considerable cost savings, and the Perc-Rite components cost $87,000 for 25,000 gallons per day. Any other disposal system still would have required larger pumps, control mechanisms, other things that very well could have been close to this number anyway. So by switching over to Perc-Rite at a very low number, they saved all of this. Moving on, so there's going to be more case studies here because a lot of the points that we talked about earlier are really developed through some of these case studies. So thank you for listening to these. So case study number 6, Graniteville Woods in Westford, Massachusetts. residential new construction subdivision of 43,500 gallons per day. Additional flow was granted, was able to be achieved when Perc-Rite was chosen as the disposal mechanism. The site is a former granite quarry, so everybody's ears should perk up just based on that. It was what's called a 40B requirement under the Massachusetts guidelines, so it was cluster development with some low income parts to it, so there were a lot of open space requirements that needed to be maintained. 11 randomly placed, all different size and configured zones placed throughout the site. It started as a primary effluent discharge system. Like other examples we've talked about, treatment was phased in, and it was built and started up about 10 years ago. So what were some of the site constraints here? 140 acres of mostly bedrock, okay? A lot of blasting here. Open space was a requirement for permitting. You had a perched water table at about 3 feet. In order for the developer to kind of make money on this project, he needed 20,000 gallons of permeable flow to be viable. So that was kind of like his break-even point, or the point for which that it made sense for him and his funding for that matter. All of the other, and I'll use my quotation fingers here, conventional leaching options that were looked at fell short of that 20,000 gallon per day number needed. So this is, again, thank you, Google, for this image. And this is the entryway of the subdivision. So a lot of the open space is at the front end, just to make it welcoming. You can see a pond here. The treatment building is here. And then this is a series of zones here, series of zones here. So a lot of the backyards of these housing units are open space designated for disposal. And here is just what the kind of the zones look like. They're all very different shaped. They're oriented differently. So you have tubing being pulled along this contour, then it changes here. So you have grade changes, blending in, all very achievable through Perc-Rite Drip Dispersal. So here's a before and after. The treatment building looks like a nice barn, tubing that was pulled in, connected together, and then the after picture. So you can see how nicely everything looks and used as an open space concept for the development. The hydraulic unit located inside the treatment building, submersible pumps. These are, somewhat larger. These are 5 horsepower pumps because there is a kind of a lift and distance component to this site. And then the zone valves were placed at the beginning of each zone manifold. So these are actually run in the ground and open and close at the point because the zones were all really all over the place. This was a better way for construction. So in summary, what were some of the benefits of choosing Perc-Rite for this case study? They got 43,500 gallons per day of flow, where they couldn't even get 20 for any other options that were evaluated. So more than double of that minimum amount to make it viable. So let's just say the developer was very, very pleased with what they're able to achieve on this site. We discharge primary effluent up to that state threshold of 10,000 gallons per day. The first units that were constructed and occupied and sold under this primary effluent discharge were sold, and the proceeds were used to fund $1.5 million in just treatment components, not just the building, but the actual membrane treatment system. Those 11 zones throughout the space, to keep that open space, Again, less time for installation, considerable cost savings. The Perc-Rite components were $150,000. The treatment system was $1.5 million. The ability to discharge 10,000 gallons per day saved the developer all the interest costs and carry costs on these construction loans, not to mention the additional flow that was afforded to them and the less fill material to build the system. So $150,000, although I don't want to dismiss it as being insignificant, is extremely insignificant in the overall cost and budget of a system of this scale and a system with this type of project of this type of possibility. So I'm going to pause and take a look at my question tab here. So question was, is the orientation of the drip holes critical? If so, how can you ensure that the tubings don't twist? Great question. So because all the tubing is pulled in parallel with contour, and even during the extruding process of the plastics when making the tubing, some of the orifices can be oriented, slightly askew from all, in one direction. Not a problem, because the tubing will drip whether the orifice and emitter is facing up or down or sideways. During the purging process, when the pump shuts off, most of the emitters will be facing down. Some of them may be facing the side, but all the effluent will find its way out of the tubing. So it's not critical, but we do try our best to pull it in so that the most of the holes are facing down. So, good question.
Rob, can I pipe in on that for a second?
Of course, Brian.
Okay, so the emitters, the intake of the emitter is just about dead center in the middle of the tubing. So like you said, it does not matter if the emitter is facing, 6 o'clock, 12 o'clock, 3 o'clock, or 9 o'clock. The intake is dead center, so it's still going to drip out as if it was facing in any direction.
Thank you. Operation and maintenance, sustainability. So let's look at it again through that number just below the state threshold and just above. So for primary effluent discharge, all of our hydraulic units that we're talking about today have disc filtration more than capable of handling primary effluent discharge. So we just want to put that out there. You don't have to make anything special when it comes to Perc-Rite if you're choosing to start with primary and then segue to treated, or just stick with primary for that matter. So typically, we will recommend quarterly routine site visits for systems of these size for primary effluent discharge. Sometimes when you deal with campgrounds and its seasonal flow, we can scale it back to semi-annual. Think about a startup at the beginning, like a week or two before camp opens, and then a week or two after camp ends. So that's, sort of the frequency there. Oakson will provide an O&M manual for all your projects. Okay, so whether it be one that's kind of in the can for very typical type of applications under this area of discharge, or if you need something more specific for those seasonal campgrounds to direct the folks on how to shut down the system for off-season, or perhaps any winterizing because electricity is shut off to the camp. So we will provide guidance in those instances. Oakson has a list of already trained service providers that cover the New England region. So we're happy to partner you with those folks that do this service, or many cases I should say, let me back up, where your state jurisdiction allows this to happen. Some states don't allow those outside the wastewater industry to perform wastewater maintenance. But in some jurisdictions where the caretaker for a camp or a site or the maintenance crew for a building can be eligible to maintain the Perc-Rite system. Oakson is more than happy to train them, give them personalized training, and then follow up with them as needed as a lifetime consultant to make sure that as new staff come on, that everybody's up to speed. So we're maintaining a kind of a lifetime relationship in this case. For larger systems where treatment facilities are a part of it, we look at it as a partnership. So 9 times out of 10, the facility, or 99 times out of 100, the facility operator who's maintaining that membrane bioreactor is going to maintain the Perc-Rite system. We'll give them customized training. We'll provide a customized O&M plan to fit within your permit requirements. Again, that O&M manual is a component, and most of the time here, it's very customized for this particular size project. We will follow up on a yearly basis for typically the first 3 years of operation to make sure that the staff has absorbed all of this training and is confident with what is going on. Or again, new staff come in all the time. We're going to get everybody up to speed. And again, we maintain that lifetime consultant point of view for all of our projects. Here's some examples of some of the O&M aspects of what's included here. So you'll see, disc filtration, cleaning or whatnot, or checklists to help the caretakers or crew of components to comply here. Part of this section of the presentation was talk about sustainability. And I can talk about sustainability for commercial projects for about a 10 to 11 year window. But I thought Brian might want to chime in here and talk about how some of the earlier systems in the late 90s for the commercial systems that American did in different parts of the country have been performing. So Brian, you have anything you'd like to add here?
Yeah, thanks, Rob. Yes, like we said, there's some of these systems that are on the commercial end have been operating for 25 years or so now, and happy to report we're still using the same drip tubing that was plowed in 25 years ago. Still using the same filter rack, same control panel, but just like any system, yeah, we've had to replace some solenoids in the control panel, maybe some bulbs and contactors, breakers. On the filter unit, yeah, you have a good illustration there in the center there of periodically cleaning the filters. Yes, once in a while they need to be done. There's some gaskets and O-rings and other small components that may need to be changed out once in a while. But like I said, 25 years and counting, no signs of slowing down. So it just that routine maintenance that you talked about is important to keep everything functioning, and we'll just see how far we can go with it.
Thank you. So I'm going to kind of fly through some additional case studies here, just so we're getting near the end of the presentation. So not to say that they're less important, but some of these have very specific aspects of advantages that I want to share with you. So this is an ongoing project right now, 22,000 gallons per day at a school district in central Maine, the Bonnie Eagle Middle High School. It has an existing treatment facility, okay? And currently it has an overboard discharge permit into a nearby river. It's a very wooded site bound by streams and wetlands and native species of bats and other things that are very important to the ecological aspect of the area. And construction began this past fall, and we actually we're pulling the tubing in, I believe it's April 9th. So that's coming up real soon. So what I wanted to share with you is a couple of drone captured pictures. The drone is over the school right now, and you can see the existing treatment building here and an access road into the woods. Here's a little further on, you can see some of the clearing required to build in the drip zones. And the only reason why clearing was required here was because the induced groundwater required the system to be out of the ground just a little bit. Here is the drone from the other perspective, looking back at the school system. So this is an ongoing project. And I don't want to, I'm not going to call out who the engineer is, but I wanted to give you, in that person's words, some of the evaluation process on why Perc-Rite was chosen here. So these are actual quotes given to me in bullet points from the engineer. So based on the evaluation of all options, drip dispersal was recommended and chosen at this site for the following reasons. It was the least environmental impact, able to meet all of the no disturb buffer areas to the stream. It minimized the impact to the existing streams and wetlands. It was a significantly reduced impact to the vernal pools. And ultimately, they found out there was no impact. The tree clearing was minimized because we can put drip on a sloping site. It was the least total construction cost, much less fill and sand due to the footprint and the ability to work on the sloping terrain. These are not my words, so I just wanted to reiterate that. And then finally, cost consideration. So again, not my words. The chamber system, so they looked at chambers, estimated would have increased the cost by approximately $150,000 to $200,000 or more because of the chambers required to be installed on a flat surface, additional fill material required for that purpose, more permitting required because culverts and access roads had to be maintained differently for chambers, an increased environmental impact, and increased waivers to be inside of those setbacks. So again, I'm not going into a lot of detail on this project because it hasn't been fully constructed yet, but I anticipate adding to this presentation at the end of the year and in future years. But again, these are just like your colleagues out there, these are in the words of the engineering team who ultimately decided to use Perc-Rite Drip Dispersal. Here is the hydraulic unit being installed in the building. Second example, the Easton Housing Authority in Easton, Massachusetts, 27,600 gallons per day. This is an existing low-income housing facility subsidized by the state and the city. Multiple failed systems, on-site systems that need to be repaired. Very limited, already built-out footprint. Budget concerns was number one here, obviously because it's a subsidized community. They wanted to minimize the pumping and hauling of the waste during the construction because that's a cost that's impossible to recoup. It was built about 6 years ago. So here are the areas of the drip dispersal fields, and they were also the areas of the failed system. So we had to replace in kind in the same footprint as was available. All of this other area is unavailable. This is not part of the facility. None of this was part of the facility. None of this was, even this area was owned by someone else and they didn't want to sell it to the facility. They had a small nook here that they built a treatment facility, and here's all your tankage. So all in this area. So what was decided was they used the roads to reestablish a new collection system to bring all of the waste down to this one point here. Then one by one, first they built the Perc-Rite components inside the building, connected to the force mains, and then aggressively took areas offline. Now this flow is being diverted to holding tanks, and then the drip zones were built and then put on commission. All future flow that was diverted were able to pick up the zones that were built in place. You can imagine, so it was just kind of bouncing around a little bit, but because of the unique nature of Perc-Rite and the ability to zone and turn zones on and off, that was achieved. So here are the zones being built, and it's all in sand fill because all of the failed systems were removed. And here is the 6-zone hydraulic unit being plumbed in the treatment building. Madison Place, Southborough, Massachusetts. New construction, high-end residential apartment complex, and it happens to be the exact same number, 27,600 gallons per day. This rendering that you might see in some of our material is actual rendering from the Madison Place complex. It originally started as a chamber system. There's significant slope here that it's hard to see by the rendering. The main achievement here was they eliminated an 18-foot high retaining wall that would have run about 250 feet. So you structural engineers out there, imagine the steel support and tiebacks required to engineer and build an 18-foot high retaining wall. It was constructed in 2013. Thank you, Google, for this image showing the constructed drip dispersal area. The complex is built on a very busy road in the technology belt of Massachusetts. So this east-west road is very well traveled, and these apartment units are 100% occupied since day one. There's a retention pond here, another resource area here. So you can imagine what an 18-foot high retaining wall would look like. Even, you have an existing gas station here along the road. Thank you, Google, for this street view image. So you can see the entire drip field very gently rolling with the existing contour here. So you can actually see the basement level of all the buildings. And excuse me for my crude, I'm not very skilled here at these things, but this is what I would consider an 18-foot high retaining wall that would extend more in this direction, but you can see what the impact would be to the look of the development from the road and maybe the aesthetic appeal driving by for folks that would want to live there, and the amount of fill that would be needed to backfill that area of about 225, 300 feet long. Again, hydraulic unit inside the MBR treatment facility. We have some manifolds being constructed and tubing being pulled into existing grade. The developer who I called recently, who ultimately sold the development and wanted to thank me and said, Rob, you can call me anytime. Because of Perc-Rite, I saved $325,000 in wall engineering, construction, and fill material, but also because of the tiebacks of the wall, I would have lost 7,000 gallons per day of flow and would have lost the ability to construct another apartment and a half. So he said anytime that I want to call him, he's happy to take my call. Any questions? So in closing, I wanted to just say that if you wanted to consider Perc-Rite Drip Dispersal, these are some of the areas that you should look at. If you have an existing direct discharge permit that you need to go subsurface, perhaps in some of the northern states where spray irrigation is still a component for effluent disposal, but there are challenges for year-long operation, we can go subsurface with drip in that same area. If you have lagoons that you need to get rid of and discharge into the disposal area, Perc-Rite's a good choice. Sloping sites, wooded sites, sites impacted by wetlands or environmentally sensitive sites, all examples of why you may choose Perc-Rite Drip Dispersal. If you have to repair or upgrade an existing community system that's failed and maximize your footprint, Perc-Rite is a great way to bring into the fold to minimize any disturbances to the residents. If you have a rest stop or a gas station that you need to kind of pump up into an adjacent wooded area or a rest or an open space rest area, Perc-Rite would be a good choice. Campgrounds, golf courses, schools, municipalities. There really isn't any place you wouldn't want to have Perc-Rite drip dispersal, but just these are some of the examples of what Oakson has worked on over the last 15 years. And here is an existing golf course on Nantucket that was built about 12 years ago, that is just under that threshold, has a full restaurant, grease traps, and nonetheless, and it's thriving. So you can, I have a video on this one if you'd like to learn more about it on our website. So earlier I asked you, why consider Perc-Rite drip dispersal for large flow projects? I'm gonna now turn it around and say, we ask you to please consider Perc-Rite drip dispersal projects for the following reasons. It's widely accepted at the state level. There's really no regulatory hurdles. All of the state agencies are very, very familiar with Perc-Rite and Oakson and in some respects, American manufacturing. There is a considerable cost savings that we showed you throughout this presentation. And earlier we discussed and then Craig, very well described the environmental protection and nutrient removal aspect with Perc-Rite drip dispersal, small micro doses, oxygen-rich soil, etc. So on behalf of Brian Allen at American and Craig Eindel at Waite Eindel Environmental Management and me at Oakson, thank you very much. You're going to see a survey as part of the follow-up to this presentation. One thing I didn't mention earlier were credit contact hours. Because this is a regional-based presentation and I typically get my credits through the state regulatory officials, I did not get an answer from all of them just yet. Vermont has said yes. I'm pretty sure Massachusetts is saying yes. I ask you to reach out to me in about a week if you would like to inquire if you're eligible for credits, and I will provide you with your own certificate. So folks, thank you very much. We hope you enjoyed the presentation, and we hope to see you at a project down the line. Have a great day.